Okay, so we've talked about solutions and we've talked about aqueous solutions. In this chapter, we are going to talk about aqueous solutions. I can tell you right now, we are not going to talk about colligative properties. So we'll define what they are, but in the amount of time we have left, the important piece that I want you to get is really behavior of compounds in aqueous solution, because it's really important. It is critical to the acid-base stuff, which we are not going to get to do. But if you're going on in chemistry, which many of you are, if you've got the background of the aqueous solution behavior, then the acid-base stuff is easier. So I want to at least get you that. That's all we can do here. Okay, well, let's talk about dissociation. Has anybody here ever dissociated themselves from a former friend? Like, you know, I think that kid's bad news. I am going to dissociate myself from this entire business. Don't want anything to do with it. To dissociate, to move apart. And when we take an ionic compound, so give me an example of an ionic compound. Name me your favorite ionic compound. Okay, I had some nice sodium chloride at lunch. Sprinkled on my little wrap. Anybody else got another? And actually, you know what? Let's just use NaCl. So we've got this lovely little ionic compound. What's holding it together? Habit. Magic. Elves. The promise of ice cream. What's holding it together? Promise of ice cream. That's what's holding many of us together. So we have sodium 1 plus, chlorine 1 minus. What's holding them together? What kind of bond? An ionic bond, yeah. So it's the attraction of oppositely charged particles is holding them together, and that's really powerful. Well, what's interesting, and you know that sodium chloride is very soluble in water. You have dissolved sodium chloride in water. You may have done it as a saltwater rinse if you had like a mouth sore. What happens when we dissolve sodium chloride in water? What is true of water? Let's draw Mickey here. Here's Mickey. What's true of Mickey? Mickey's a polar molecule. So water also has areas of partial charge. And because of that, water gets in between the sodium and the chloride, and it surrounds, and this illustration is an attempt to do justice to that. So remember, the sodiums are positive. Well, you get a bunch of water molecules with the little negative areas surrounding the sodium, because they're attracted to that sodium just like chloride is. Well, those chloride ions, you can't see that says chloride, get a bunch of little positive ears pointing towards them. Because again, they're every bit as attracted to that chloride ion as the sodium was. So water actually gets in between. So what happens when you dissolve all these sodium chlorides into water is that the water actually separates them. And they move apart. That moving apart of ions in an ionic compound when it's dissolved in water is called, guess what? Dissociation. So they dissociate. And we still have sodium ions, we still have chloride ions. They're just no longer holding hands. They're no longer standing shoulder to shoulder. Water has come between them. So we show dissociation using what's called a dissociation equation. And we will practice writing a couple of these. So let's name another fun ionic compound that everybody loves. Ooh, I know. What'd you use to make soap? You don't have to lie about it if you don't remember. Lie is sodium hydroxide. Sodium hydroxide. Okay, so we have solid sodium hydroxide. And you did this. This is what you did when you put your sodium hydroxide into water and created a sodium hydroxide solution. That's it. That's it. And we very often, and sometimes I slip and forget, but we very often show that little H2O over the arrow to indicate this is not a chemical reaction. This is not a decomposition reaction. We're not splitting this into simpler parts. We're just dissociating it. So it's not a chemical reaction. You don't have any new substances happening. We just are splitting up the ions. So that's a dissociation equation. Now, stoichiometry. If we take, we're back to sodium chloride, if we take a mole of sodium chloride, and that should have a little H2O over it, and we dissociate it, we get a mole of sodium ions and a mole of chloride ions. Okay? So 1 mole of sodium chloride yields 1 mole of sodium ions, 1 mole of chloride ions. That sounds about as simple and basic as anything could, doesn't it? So let's look back to our example here. If we have 1 mole of sodium hydroxide ions, how many moles of sodium ions do we get? 1. How many moles of hydroxide ions do we get? 1. Here's the trickier question. So 1 mole of sodium hydroxide yields how many total moles of ions? 2. Okay, so we said if we have 1 mole of sodium hydroxide dissociating, we get 2 moles of ions out of it. Let's look at something a little bit maybe trickier. So iron 3 bromide. What would the formula be for that? FeBr3. It's an ionic compound. It's a metallic ion and a halogen. So what if we just, and this is, if we take this as a solid, what if we dissociate this? What do we get? Well, we get a mole of iron 3. How many moles of bromide ions do we get? 3. Because remember, bromide is a 1 plus. For every 1 iron ion, say that 10 times fast, there are 3 bromide ions. So for every 1 mole of iron ions that we get, we're going to get 3 moles of bromide ions. Okay, so you have to look at the formula. These subscripts will tell you how many moles of each ion you're going to get. So let's do, what the heck is that? Ammonium what? Sulfide. Yes, good. Okay, so how many moles of ammonium ions do we get out of this? If we dissociate, if we dissolve in water 1 mole of ammonium sulfide, how many moles of ammonium ions do we get? 2. So we get 2 NH4 1 plus, and that ion doesn't break apart. We're not talking about anything that would break apart an ion. We're only moving the individual ions apart. If we have a polyatomic ion, it stays together. So we get 2 moles of ammonium ions and 1 mole of sulfide ions. Okay. So those are dissociation equations. They're not that hard. What is that stuff? Al2SO4 3 times. What is it? Aluminum sulfate. If we dissociate that, how many moles of aluminum do we get? Vote with your fingers. 2. So we get 2 moles of aluminum 3 plus in aqueous solution. How many moles of sulfate ions do we get? 3. So we get 3 moles of SO4 2 minus, also aqueous. So if we dissociate 1 mole of aluminum sulfate, how many total moles of ions do we get? We get 5. We get 2 aluminum, 3 sulfate. Level of comfort from 0 to 5 with writing dissociation equations. Okay. Yeah, it's fairly simple. I would expect that you're all at a 4 or a 5. So this is the first step. Let me explain how we're going to handle chapter 14. There's really one big skill in chapter 14 that is what supports you when you go into doing acid-base stuff if you go on in chemistry. And that big skill is writing net ionic equations. Okay, so net ionic equations. What supports that skill are 2 other skills. So first, you have to learn how to write a dissociation equation, which I think you all just did. And second, you have to learn how to predict solubility. Once you have this one and this one, writing net ionic equations is about the simplest thing you'll ever do. Okay? So I think you've pretty much just conquered number 1. I'm going to give you some practice problems out of the book for you to do on your own. We're going to do some solubility prediction. I'll give you some practice problems from the book, and then we'll have a quiz on that tomorrow. Okay? After our quiz on that, we're going to start learning. Basically, the only thing that we're going to be able to do out of this chapter really is I want you to be able to do this out of chapter 14. Because that will help when you go on to acid-base stuff. The acid-base stuff will make much more sense if you understand this concept. So 1 skill down, 1 to go, all leading to the big thing. So let's do solubility practice. Or let me give you problems for dissociation. On page 426 at the bottom of the page, practice number 1, A through C. It's just 3 problems. They're really simple. And the answers are there. So you can just look at the answers. You can cover them up while you do the problems and then just see if you've got it or not. Okay, moving on to predicting solubility. Okay, so also in order to do net ionic equations, we have to know what's soluble. And solubility is one of these things where most people like it because there's just a set of rules, and you look at those rules and you determine should this dissolve in water or not. And the solubility that we're talking about, these are all things solubility in water. So you can do charts for solubility in gasoline, oil, alcohol, anything, any other kind of solvent, but here we're just talking about water. So if you look at page 427, there is a chart on the bottom of the page that says General Solubility Guidelines. And I assume that you can read. I know you can all read. So I'm not going to read them to you because that's insulting. But what it gives are general guidelines, and compounds are named based by how they are grouped. So for instance, ammonium nitrate would be considered a nitrate. Okay? We would say, oh, that's a nitrate, so's sodium nitrate, so's potassium nitrate, so's barium nitrate. Those are all nitrates, nitrate compounds. Ammonium compounds, so ammonium nitrate, ammonium chloride, ammonium bromide. All of those would be ammonium compounds. So we're looking at sort of general categories. We're going to actually just go down and practice this, and there are 8 of you. There are 5 examples here, and I'll make up 3 more, so everybody gets one. All right, the first one, ammonium nitrate. Everybody's going to do one. Who wants to be the first guinea pig? Should we do this one together? We'll do this one together. I won't make you a guinea pig. Okay, so if we look at the guidelines, the first general solubility guideline says most sodium, potassium, and ammonium compounds are soluble in water. Is this a sodium, potassium, or ammonium compound? Yeah, it's ammonium nitrate. It is an ammonium compound. Okay, let's keep looking to see if there are any exceptions. Rule number 2, most nitrates, acetates, and chlorates are soluble. Is this a nitrate, acetate, or chlorate? Yeah, it's a nitrate compound. So at this point, I'm going to say this is soluble in water. Let's look at the next couple rules. Number 3, most chlorides are soluble except those of silver, mercury, and lead. Lead 2 chloride is soluble in hot water. Do any of those things apply to this? Is it a chloride? Is it a silver, mercury, or lead compound? No, we can ignore all that. 4. Most sulfates are soluble except barium, strontium, and lead. Is it a sulfate or does it contain any of those? No. Disregard. 5. Most carbonates, phosphates, and silicates are insoluble except those of sodium, potassium, and ammonium. Is it a carbonate, phosphate, or silicate? No. Most sulfides are insoluble except those of calcium, strontium, sodium, potassium, and ammonium. Is it a sulfide? No. So we found nothing but rules number 1 and number 2 that apply to it, and both of those rules would indicate that this is soluble. So that's what you want to do. You want to run through these things and look for something that says, yes, everything that's like this thing is soluble, or everything like this thing is soluble except if it contains da 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 da. So who wants to give number 2 a shot? You can work, I'll tell you what, you can work as pairs. Work as a pair. And what I want is which rules apply to this, and do you think it will be soluble? So we have a unanimous soluble in water, and that is based on rule 1 and 6. That's all you're doing, is looking down through there. So I'll tell you what, we'll do the same approach for that next compound. I'm not even going to say what it is. So you can work in teams again, or you can work solo, but everybody do it, and then we'll take one team who will publicly announce their findings. You say insoluble in water, and based on what rules? Okay, so we're claiming insolubility based on Rule 5. Most carbonates, phosphates, and silicates are insoluble except those of sodium, potassium, and ammonium. It is a carbonate. It is not one of the exceptions to carbonate solubility. So, and yeah, this is based on rule number 5. That's exactly how this works. But you do have to be able to name the compound. Do you know what calcium carbonate, where calcium carbonate's found in a large quantity? The shells of marine organisms. If calcium carbonate was soluble in water, would life be very different for them? Yes. Yes, it would. Okay, next one. AgCl, I'm not saying it. Work together, and then one group gets to announce. So our folks up front here say insoluble based on which rule? Based on rule 3. Most chlorides are soluble except silver. So yeah, this is insoluble based on rule 3. Okay, and our last one, BaSO4. So we have somebody saying insoluble in water based on rule 4. And rule 4 is most sulfates are soluble, but wait, except those of barium, strontium, and lead. Okay, so it's pretty easy. I'll give you a set of practice problems for this, and you can get started. And these will be right out of the chapter review. Chapter review number 2. And there are a bunch of different parts, so you get lots of practice. And some of them actually, sadly, we've just done, but there are plenty that we haven't done. So, actually, you know what? We'll say number 1 also. That's a quick, simple one, but it goes to the dissociation stuff. So, that's the homework. You can start on it right now. You'll have a FIP tomorrow over dissociation and solubility. Yeah, and also the practice on 426, number 1, A through C, that's also part of the homework. So, okay, I'll give you time to practice and work.